Hi, hello everyone. This is Dr. Chiranjeevi Manike, Professor and Head of Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. As part of data mining video lecture series, in this lecture we are going to discuss two concepts from the third unit, which I forgot to mention. One is a Bayesian belief network, another concept that we are going to record in the next lecture, how to train the Bayesian belief networks. So in this lecture, we are going to discuss basic concepts related to this Bayesian belief network. So Bayesian belief network is an advanced technique for the data classification, which is unlike naive-based classification, where the naive-based classification, there is an assumption called as a class conditional independence, but which is this Bayesian classifier is not like naive-based classifier, which do not assume the class conditional independence. We'll see in detail about this property later. And it is a probabilistic graphical model which, unlike a Bayesian classifier, allow the representation of dependencies among the subset of attributes. The naive-based classifier makes the assumption of class conditional independence. So what does it mean by this class conditional independence? So given the class label of a tuple, the values of the attributes are assumed to be conditionally independent of one another. There is no dependency among the attributes of, like if you take any tuple, the class label of a tuple and the values of the attributes. Like suppose there are different tuples like x1, x2, x3 and so on. Xn number of tuples will be there in a data set, and if you take any data set and the class label of that tuple, the values of the attributes, there are like attributes a1, a2 and so on, n attributes would be used to describe this a tuple or a data object. These are assumed to be conditionally independent of one another. So mainly that is, as we already discussed in that naive-based classifier, that is mainly used to simplify the computation. So when this assumption holds true, then the naive-based classifier is the most accurate in a comparison with other classification approaches. So, but in practice, in the real world, the dependencies can exist between the variables. So how to handle if there is a dependency among the variables? So one solution is a Bayesian belief networks. This Bayesian belief network specify the joint conditional probability distributions. They allow the class conditional independence to be defined between the subsets of variables. So they provide a graphical model of a causal relationship on which learning can be performed. So trained Bayesian belief networks can be used for classification. We'll see how we can train this Bayesian belief networks. The Bayesian belief networks are also known as a belief networks or Bayesian networks or the probabilistic networks, etc. For brevity, we will refer to them as a belief networks. And in this, to explain the we are going to take an example. That example is obtained from this Hanen-Camber textbook. I would like to give a brief idea of this figure 9.1, the simple Bayesian belief network. It is an example which is obtained from the source, this source. So that you can get from the textbook Hanen-Camber. So let us see the definition, how we can define a Bayesian belief network. A Bayesian belief network is defined by the two components mainly. The one is a directed acyclic graph and set of conditional probability tables. So from that example, I obtained these two diagrams A and B, and this represents the directed acyclic graph, and this is a conditional probability table. It's a conditional probability table for a single variable that we will discuss in the coming slides. So let us understand what are the about this directed acyclic graph, because it is A belief network is defined by mainly these two components: directed acyclic graph, DAG, and set of conditional probability tables, CPT for short. So here, each node, like the smoker is a one node, and family history, lung cancer, positive X-ray, and these are all the different nodes. So each node represents a random variable. Here the node represents a random variable. Each node represents a random variable, and the arc represents the probability, conditional probabilities, and there is a dependency between the nodes also. The arcs, like the family to history, it is a directed acyclic graph. So the direction, that is, this is represented from the smoker to emphysema, etc. So here, let us take one conditional dependency, like having lung cancer, that is depends on the smoker, whether the customer is a smoker or non-smoker, and also whether a customer has the family history of lung cancer. So that is a conditional dependency. And coming to this set of conditional probability tables, that is another component of the Bayesian belief network, and this is one conditional probability table for this lung cancer, LC, short name LC, and this is lung cancer, and there is no lung cancer. And we will discuss what are these values, how to get these values. All these are all the probability, conditional joint probability distributions. So in this directed acyclic graph, as I said just now, each node represents a random variable, and there is a relationship called as the parent and the child relationship. Like suppose the smoker, here let us take this relationship between the lung cancer, the node, and the another node is a smoker. So here this is a parent node and this is a child node, and this is also called as a descendant, and this is also immediate predecessor or the parent of lung cancer. Similarly, the family history is a parent of lung cancer. And coming to this conditional probability tables, so here this is the conditional probability table for the lung cancer. So for this variable y specifies the conditional distribution, that is probability of y given parents of y, where parents of y are the parents of y. Here the conditional probability for each known value of a lung cancer is given for each possible combination of the values of its parents, like the family history, yes or no. Here negation represents, so having lung cancer and not negation represents. Similarly, the values for this lung cancer or other attributes, other random variables, like family history, yes, whether they have a family history or not, whether the customer is a smoker, the patient is a smoker or not. Like the combination of values would be taken for each parents and their children to make this conditional probability tables. So let x equal to x1, x2 and so on xn be a data tuple that is described by variables or attributes called as y1, y2 and so on yn respectively, and this allows the network to provide a complete representation of existing joint probability distributions with this equation, that is probability of x1, x2 and so on xn equal to, that is a product of that is probability of xi given parents of y, where I equal to 1 to n. Here the probability p of x1, x2 and so on xn is the probability of a particular combination of values of x. X is a data tuple in any data set here, and the values for this probability of xi given parents of yi correspond to the entries in the CPT for yi. So yi is one attribute or a variable. A node within the network can be selected as a output node. That is, so far we discussed about the input also, but in another node, another category of node within the network that could be selected as an output node that represents a class label attribute. So there may be more than one output nodes. So a network can have more than one output node. So various algorithms for inference and learning can be applied to the network. So rather than returning a single class label, in this case like single class label, the classification process can return a probability distributions. That means that gives the probability of each class, as we discussed in the Navy base conditional probability distributions. Like suppose if you take any tuple, and if there are two classes like class I and J, and then it would also returns to what is the probability that this tuple belongs to class Ci, and what is the probability that this tuple belongs to another class Cj. So belief networks can be used to answer the probability of evidence queries. For example, what is the probability that an individual will have a lung cancer, given that they have both the positive X-ray and dyspnea? And most probable explanation queries, example, which group of the population is most likely to have both the positive X-ray and the dyspnea? And the belief networks have been used to model a number of well-known problems. One example here is like genetic linkage analysis. In this case, mapping of genes onto chromosomes. By casting the gene linkage problems, that is in terms of inference on Bayesian networks, and using the state-of-art algorithms, the scalability of such analysis can be advanced considerably. So other applications that have benefited from the use of Bayesian belief networks includes computer vision, that is mainly the image restoration and the stereo vision, document and text analysis, Bayesian support systems, and the sensitivity analysis. So the ease with which many applications can be reduced to the Bayesian network inference is advantageous in that it curbs the need to invent a specialized algorithms for each such applications. So thank you for watching this video.